All right, ladies and gentlemen. So, I hope you are having a great day so far as you get started on this lab. So, this is for those of us who were not able to attend the live online lab on Zoom. So, once again, hopefully, if you've not already done so, you've watched the first video that I created, just kind of introducing the idea of electric force, the idea of charges, and kind of the idea of what exactly happens if you put two charges that are similar next to each other and two charges that are opposite. Just to kind of briefly summarize, literally in one sentence, it's the age-old thing you've always heard: opposites attract. If I take something that is positively charged and something that is negatively charged, and I put them near each other, they are going to attract each other. If I take two things that are the same charge, or two positives or two negatives, and I put them near each other, they are also they are going to repel each other. All right. And what we're going to do today in this lab is we're going to actually figure out exactly how much they're going to push each other away or pull each other together. All right. So, if you could please, I would love you to be on the Google Doc that is currently on the screen. All right. So this is the second page of the Google Doc on Canvas. Now, what we're going to do is we're going to basically talk about the idea that this is just one extra force. So we're just basically going to explore a little bit about this new force and kind of how it seems to interact with other objects, how it seems to kind of work its way into what we know about forces. So the first thing we're going to do is what's fascinating about this force and what's kind of important is that it is not a contact force. So in order to exert an electric force, I do not have to be touching anything. Okay, which is different than the other forces we've talked about with the spring force, normal force, friction, or applied forces. They all have to be in direct contact. The only other force in mind, actually, that we've talked about that does not involve touching something is gravity. All right, and the first question I have on your lab is just kind of what physical quantities affect the gravitational force on an object. I already kind of put the answer there, but take a sec just to kind of think about it. All right. So, honestly, if you remember Newton's law of gravity, which was kind of that very weird formula that says the force of gravity between two objects is dependent on the mass of one object times the mass of the second, divided by how far away they are from each other squared, and then you multiply by that big G, that weird constant that was a weird number. All right. But what mattered is that the two things that affected how strong gravity would pull on another object was how massive the objects were and the distance between the objects. All right. If you made an object more massive, it had more gravitational pull. And if you changed the distance, if you pulled them farther apart, it actually weakened how much gravity would pull on the two of them. Okay. Now, we're going to do the exact same thing today, talking about electric force. So, what I would like you to do, please, is I want you, if you're on the Google Doc, to click on this little hyperlink that says Electric Force Lab. All right. This is going to open a screen that looks like this. To say electrostatic force mini lab with numbers, you're going to hit begin. What I would suggest first, just to make it easier, is I would decrease the charges to about whatever, maybe the lowest number. Honestly, that'll be more than enough. So decrease it to the lowest number. All right. Now, what we are going to do is you're going to kind of go through and you're just going to literally answer these first four questions. You notice I already made some observations. I want you to go and make your own observations, and we'll come back together and talk about it. So what I want you to do right now, please, is I literally want you to go through and answer these three questions. So where it says first, I want you to play around, then what happens to the force if you double, and then what happens to the force if you half. I want you to answer these three questions, okay? And that should take probably about maybe 5.5 minutes at the most. So if you could, I want you to pause the video right here, play around with this lab, write down your observations, and then we're going to come back and talk about exactly what all this means. So you can stop where it says all the observations you've made make a fancy formula. Okay, so at this point, pause the video, go through and answer those three questions in the lab, and then you can unpause and we'll talk about what you saw. All right, so at this point, hopefully you've gone through the lab and answered these three questions. So let's talk about some things that we hopefully saw. Okay, so if you were just playing around with these two things, what you're doing, this whole lab is basically you are taking two metal spheres and you are changing the electric charge on them. Okay, that's one of the things you can do. So in this case, these are positively charged. That means they have more protons than electrons. All right, so that means we've taken electrons away, and you're basically just making the charges, probably in this case, you're just making them greater. All right. Now, hopefully, some things you observed is just like things that honestly, if you think about it, make total sense. If I put more charge on a sphere, so if I increase the charge, the force between them increases as well. And of course, vice versa, as I drop it, the force gets smaller. The distance, if you played around, because you actually find out you can move these as well. If you change the distance, you can also affect the force between them. In this case, the farther away, it seems to have less force. Close together, more force, which also, if you think about it, makes a ton of sense. If I have two things that are both positively charged and I try to hold them near each other, they hate that. They do not want to be near each other. All right. And then the other thing, this one's a little bit, hopefully you might have noticed it in the back of your mind, didn't really think much of it. But basically, it doesn't matter if I change the charge of this object or change the charge of this object. If I increase the charge on the right, the force increases. If I increase the charge on the left, the force still increases as well. Okay, and that's just an important observation to make, that it doesn't matter which one you change, the force is still going to be effective. All right. Now, just looking at the actual numerical things that happen, I wanted you to double the charge on one of the spheres. All right, and if you did that, so you go through and we'll say we're going to do the left sphere, so it's 6.1 nanocoulombs right now. If I double that to 12 nanocoulombs, the force was originally 15, now it's about 31. That's roughly double the original. So if I doubled this charge, the force gets double. Okay, and that leads nicely to the second question, which is what happens if you double this and you double this one? So this has now been doubled. I'm going to double the thing on the right as well. All right, and lo and behold, now, remember the original charge, when all said and done, if I go, that was 15. If I double both of these, all right, that's roughly 4 times the original force. Okay, so what that means is that if you double the charge on one of them, the force will double. If you double the charge of both objects, the force is actually going to quadruple. Okay, in a second, we're going to talk about why that is when we look at the law for electric force. And then the last piece is that if you cut the distance in half, so right now it's about 42 millimeters. If I cut that to about 21, all right, we'll see the force is increasing, and in this case, 42, so it's 0.67. Actually, if you do 0.67 and you multiply it by 4, you'll get about 2.63 millinewtons. Okay, and remember, don't worry about all these little things in front of it. The general thing is all that matters. Okay, if I half the distance, I've actually 4 times the force. I've quadrupled it. Okay, which actually, hopefully, if you think about it, that should sound pretty similar to another law that we've talked about with kind of things acting at a distance. All right, so with these observations in hand, let's write down exactly how we can use them. So, for electric force, we use something called Coulomb's law, and it looks like the following. So, to calculate the amount of electric force between two charged objects, what you do is you take the charge of the first object, okay? You have to make sure it's in coulombs. What we're going to find out is that when they discovered electricity and charge, the Coulomb actually represents an enormous amount of charge because the instruments they had were very crude and they could only see a lot of charge at once. Okay, they weren't very precise. So we're going to usually use things that are much smaller than that. So you take the charge of the first object in coulombs. You multiply it by the charge of the second object, which is also in coulombs. You multiply it by something we call Coulomb's constant. Okay, and that's similar to like we did that big G with gravity. In this case, Coulomb's constant is 8.99 times 10 to the 9. And this is on the formula sheet. Okay, you don't have to memorize it, but you need to realize you have to multiply these two things by some other number as well. Then, in order to finish it, to calculate the force, you divide everything by the distance between the charges square. All right? What it looks like in actual formula form is it looks like F, the electric force, equals K little e, which just represents the Coulomb constant, times the charge of the first object, times the charge of the second object, divided by the distance between them squared. All right? Now, with that being said, there's just a couple extra things we want to talk about that are important for just understanding what all this looks like. So, The units for charge are a Coulomb. We talked about that in the first video, but just to remind you, that literally is just a measurement of how many, usually it's a measurement of how many extra electrons you have or how many extra electrons you are missing. So if you have a negative charge, that means you have extra electrons. If you have a positive charge, it means you're missing electrons. Okay? The electron has a fundamental charge. So the charge of one electron, just to give you an idea of how small these things are, is negative 1.6 times 10 to the negative 19th Coulomb. It is so small, exceedingly small. The wild thing is that the proton has the exact same charge. It's just positive, okay? And protons and electrons are very different size. So this would be something where we have a great conversation in class. Sadly, we can't, but it's just something to understand that it shows how small charges are, okay? Now, let's actually try it out. Now, I know electricity can be very strange and charge can seem really weird, but honestly, all the rules of forces still apply. Okay? This is just one extra tool to find a force, and then everything else we're used to using works out here. Okay? So, in this question, I start by having two negative charges, and they are placed so they're 2 millimeters apart. Okay? Now, each negative charge has a charge of 2 nanocoulomb, and I apologize, that should be negative 2 nanocoulomb, though it's not really going to matter when you see in the calculation. But it has a charge of negative 2 nanocoulomb. They're 2 millimeters apart. And I want to calculate how much force is the left charge experiencing. So, because these are two electrically charged particles, we're going to have to use Coulomb's law, which means we're going to use this little thing right here. And we're going to start by writing out everything that is important. So, to calculate the electric force, you start by doing the charge of the first object. In this case, it says it's negative 2 nanocoulomb. That nanocoulomb, that little n, just means it's times 10 to the negative 9 to get it to coulomb. Okay? So, what I do is I write it as negative 2 times 10 to the negative 9. That's the amount of charge it has in coulombs, times the same thing again because they're the same charge, so times 2 times 10 to the negative 9th coulomb, times 8.99 times 10 to the 9th. That's that scaling factor, that Coulomb's constant. Then you divide by 0.002 squared. That's the distance squared. Okay? And it's 0.002 and not 2 because this is in millimeters and I want it in meters. Now, I want you to plug this into your calculator. The final answer, the amount of force between the two. Actually, I'll wait a sec. So, instead of saying the final answer, you can see on the screen, I'm going to talk you through what are some common things you might run into. These questions can be very frustrating because the distances and the charges are so small that it turns into more of a calculator question than an understanding the physics of what's going on question. All right? When you do this, you have to be very sure that you put all the parentheses in the right spot. Okay? And what I would suggest is I would probably do the top row first, all the multiplication, just to make sure it doesn't get confused. Get a number, and then divide it by this. So if you plug these three things, you do negative 2 times 10 to the negative 9th, times negative 2 times 10 to the negative 9th, times 8.99 times 10 to the 9th. If you do that and multiply it all together, you should get that the answer of those three things multiplied together is 3.596 times 10 to the negative 8. So that would be, just to be clear, that's those three things that are currently highlighted multiplied together. To get the true force, you then divide it by 0.002 squared. And when you do that, you'll get that the electric force acting on both charges is 0.00899 newtons. Okay? And in this case, if I asked you to go one step further and do the direction, it would be 0.00899 newtons to the left, because we're talking about this charge, and these two are going to push each other away because they are the same charge. All right? So, hopefully that's kind of explained a little bit about how we can calculate electric forces. A lot of it, I promise, is stuff you're like, well, it makes sense. Of course, like opposite attract, like things repel. It's all based off that. And of course, once you calculate the force, you use all the same rules for forces that we've done before. Okay? So I'm going to post another video tomorrow that does some more practice with looking at these charges and forces. There's a web assign up you are welcome to get started on that talks about calculating electric force. If you have any questions, please send me an email. You do not need to turn in this lab to me. These are your notes. You do not need to give them to me at all. And with that being said, have a great rest of the day, ladies and gentlemen.